Okay, so welcome to this next video in the theory of probability. In this video we're going to discuss how to calculate the moment generating function, the MGF, of a random variable which is distributed exponentially. So a random variable distributed exponentially. So I'll say distributed exponentially with some parameter lambda. This is the setup we have. We have some abstract probability space here which consists of a sample space of outcomes, a set of events, and a probability measure. So the general, the archetypal example of a abstract probability space that we consider to be exponentially distributed is if you are waiting for a phone call and the outcome of the experiment is the time at which the phone call occurs. So of course the phone call could occur at any time, any positive real number after the starting point for the experiment. So it could take on any positive real number. Then what we consider these numbers as just placeholders. They are just symbols denoting a certain amount of time. What we then do is we have a map x, which is going to map this onto, again, the positive real numbers, and it's just going to be really trivial. It's going to map 0, well, not 0 isn't one of these, but it's going to map 1 onto 1, 2 onto 2, 3 onto 3. It's going to map every, so x is going to map any outcome s, and it's just going to map it onto itself in here. But now what this structure here is different from this one because we are assuming that this has the algebraic properties of the real numbers defined on it. Okay, and we will say that the random variable x is exponentially distributed with some parameter lambda. Now, that, if we draw out its PDF looks something like, now if it's distributed lambda, its PDF f of big X of little x, so the PDF of the random variable big X as a function of little x, and little x is well, actually little x can be any real number. It's going to be equal to 0 if x is a non-positive number, so not including negative infinity to 0, and it's going to be equal to lambda e to the negative lambda of x if x is a positive real number, so 0 to infinity. Okay, so it's going to look something like this. You don't have, the point at 0 is down here at 0, so all of the negative numbers are along here. So if I get a coloured pen, so it looks something like this, and then it has a hole. It has a hole at 0 up here because the point isn't there, even though the limit from the right-sided limit will be there, and that point will be lambda. So the right-sided limit is the limit of this, and of course as x approaches 0, this is going to converge on lambda, and then it drops down in a negative exponential way. And of course we're assuming, of course, that lambda is some positive constant. If it's negative, then this isn't a valid PDF. Okay, so now what we do, so this is our PDF here, and our CDF, our corresponding CDF, is the integral of this from 0 to infinity, and this gives the integral. If you integrate up to some negative or non-positive real number, you're just going to be integrating 0, so it's going to be 0 if x is an element of negative infinity to 0, and it's going to be equal to the integral of this, which is 1 between negative infinity and x, which is 1 minus e to the negative lambda of x, if x is an element of the positive real numbers, 0 to infinity. Okay, so that is our exponential distribution, our general exponential distribution, but we know that general exponential distributions can be standardized. They can all be reduced down to the standard exponential distribution. Specifically, there is a map, let's say a map, let's draw it here, a map T, which is going to map all of these real numbers onto another positive real number in another probability space here. And the way it's going to work is that T is going to map any little x. So let's say we've got a little x in here, which is a positive real number, and the way it's going to work is it's going to map little x, and it's going to map it onto lambda times little x. And this, if we think about what this is going to do, then if this is the, these are the possible values of the big random variable x, so this is the positive real numbers here, then if you take some little x then what it's going to do is it's going to map it onto lambda times little x. Now, we want this to be a probability space isomorphism here, i.e. we want the probability density function of the corresponding value in here to have the probability density function of the value. Well, we don't want that. That's not what I mean. We want the probability space structure on here to be the same as the probability space structure on here. So if we take any event, and we know any event can be gotten in terms of the events that. So let's say if we have an event x is less than or equal to some little x, which is if I get my pen out. That's the event that it's less than or equal to this little x here. So it's that event corresponding there. The corresponding event in here is the event that y. Let's call this. So let's call the composition of these two maps, the composition of x and t. We're going to call that new random variable. We'll call that random variable y. So y is the composition of x and then t. Okay, so the corresponding event for the random variable y is going to be the event that y is less than or equal to lambda times x, and we want the probability. Let's say that this has a probability measure. Let's call this the probability space omega double prime f. Oh dear, what have I done? F double prime and p double prime, and let's call this one omega prime, f prime and p prime. Then we want the probability p double prime that y is less than or equal to lambda of x to be equal to p prime that x is less than or equal to x. So we want the probability of this event in here to be equal to the probability of this event in here. Okay, so that says that this is the PDF. This is the PDF of the random variable y evaluated at lambda times x. We want that to equal the PDF of x evaluated at x. Okay, but we know what the PDF of x evaluated at x is. That is going to be equal to where is the PDF of CDF? Sorry, these are CDFs, not PDFs. Sorry, that's really confusing what I've just said there. We want this to be equal to 1. So just going straight to this formula here, we get 1 minus e to the negative lambda of x. Now what we say is, oh look, we've put in lambda of x, and this is our value here. So if I just let little y equal lambda of x, then we get that the CDF of big Y of little y is 1 minus e to the negative y. And then if we differentiate that to get the PDF, so the PDF of the random variable big Y is equal to e to the negative y, which is the PDF of a standard exponential distribution. So we find that this new random variable big Y is exponentially distributed with parameter 1. So that's why you can always think of you can always standardize a general exponential distribution, and you can from it derive a new random variable big Y, which is going to be distributed exponentially with parameter 1. And then what we can do is we can think about reversing this transformation. So we can think about taking T inverse, because it is a bijective map, this map here, of the positive real numbers onto the positive real numbers here. So you can think about taking T inverse, and then we could think about x being equal to T inverse and y initially. So you first do y and then do T inverse. So we can think of a general exponential distribution x, random variable that is distributed by a general in a general exponential distribution fashion. We can think of it as as a standard exponential distribution along with this linear map, because this is just going to T inverse is just going to map any little y onto little y divided by lambda. So we will be able to derive the result, the MGF for a general exponential distribution, which is x, is the random variable big X is distributed generally exponentially by first calculating it for the standard exponential distribution and then using this to transform it. Now, the reason we're going over this is you could have just easily just calculated the MGF for a general exponential distribution. So you might think, why am I going through this faff? Because it's very, very good recap to do this stuff and make sure that we're all clear with these concepts of standardization and you know, turning one random variable into another random variable. It's very good practice, because this in fact is far more difficult than working out the MGF. This is where all the understanding is, and the MGF is just a calculation, just apply a bit of calculus. Okay, so now let's work out the MGF for the standard exponential distribution y. So MGF, big M, of the random variable big Y as a function of t is defined to be equal to the expected value of e to the t of y. Now, we just apply Lotus and say that this is equal to the integral from over all values that the little y can take on. Now, of course, we know that little y can only be a positive real number, but we still integrate from negative infinity to infinity because the PDF is defined on the interval negative infinity to infinity. But of course, this is just going to reduce down to 0 to infinity because it's only defined on the positive. Well, it's not defined. The PDF is defined on the whole real line, but the only values that y can actually take on is 0 to infinity, but it's good practice still to put the integral from negative infinity to infinity. Okay, and then we will put in e to the t of now little y, so we're letting it vary over every possible value that y can take on, and then we're timesing it by the PDF of little y, which is e to the negative y dy. Okay, and we know that this reduces down to the integral from 0 to infinity because, as I say, y can only take on positive real numbers. E to the now let's put these firstly together and then let's factor out the y, and we get y times t minus 1 dy. Now, this integral is going to converge if t minus 1 is less than 0. So if t minus 1 is less than 0, then the curve looks something like this, and if we integrate it from 0 to infinity, we will get some convergent value. If, however, t minus 1, say, is equal to 0, then this curve becomes equal to this, and that's the integral between 0 and infinity in that case certainly doesn't converge. And if even worse, t minus 1 is greater than 0, then you get something that looks like this, and it certainly doesn't converge then. So what we require, in order for this integral even to be convergent, we require t minus 1 to be less than 0, which is the condition that t is less than 1. Okay, so this MGF is only going to be defined for t is less than 1. Okay, so now let's get another piece of paper. Right, so now the MGF of the random variable y as a function of t is equal, let's assume that t is less than 1, so this is equal to, we're going to use the second fundamental theorem of calculus. The antiderivative of this is e to the y t minus 1 divided by t minus 1, and then we're going to evaluate it between 0 and infinity. Now, if t is less than 1, then t minus 1 is less than 0, so it's negative. So when you take the limit as y approaches infinity, this thing goes to 0. So the first part of this term goes to 0, then we get minus e, and then we put in y is equal to 0, which is just e to the 0 times t minus 1, divided by t minus 1. So e to the power of 0 is just 1, so we get minus 1 over t minus 1, multiply top and bottom by negative 1, and we get that this is 1 over 1 minus t. And remember that this function is only valid if t is less than 1. So the MGF of y, which is standard exponentially distributed, so y is exponentially distributed with parameter lambda, 1 rather, is equal to 1 over 1 minus t, providing that t is less than 1. So it's a function only defined for t is less than 1. Right, okay, so we're now going to, firstly what we're going to do is calculate this for the generalize this and say, okay, we had our random variable x, which was exponentially distributed with parameter lambda, and you told me that x was equal to t inverse of y. So if we view it like that, then we can say, what is the MGF of x as a function of t? Well, it's going to be the expected value of e to the tx, but look at this, t inverse just says, t inverse just is multiplying multiplying y by 1 over lambda. So this is 1 over lambda times y, because t inverse was just going to divide every value of y by lambda, so it is the random variable divided by lambda. So that's what x is in terms of lambda. So we can, well, what x is in terms of lambda and y. So we can replace x with y divided by lambda in this way. So it's the expected value of e to the t y over lambda. And this is just going to be the expected value of e to the t over lambda times times y. Now, this is just the MGF of y evaluated, instead of evaluating at t, we evaluate it at t over lambda. So now we know what the MGF of the random variable y was. It was equal to this. So if we just stick that in, we get that the MGF of a general exponential distribution x is equal to 1 over 1 minus t divided by lambda. So we could multiply top and bottom by lambda, and we get lambda over lambda minus t. Okay, and this of course would require that, in this case, it would require that t over lambda was less than 1. So it would require that t was less than lambda. Okay, so that would be the condition on which this is valid. Right, so that's the MGF function for a general exponential distribution. Now, what we will turn on to is, why is this useful? Let's say we want to calculate the moments of a general exponential, of a general exponential distribution. Let's try and calculate the moments of in fact, better than that, we can calculate the moments of a standard exponential distribution, and then use the fact that the general exponential distribution is connected to the standard exponential distribution by this, which will be easier than just going from this. So this is one of the applications of a moment generating function. If I wanted to know the expected value of y to the power of some n, well, that would be before moment generating functions. What we'd have had to do was the integral from negative infinity, but of course it's only defined of y's, we're integrating over all values of y, so it would start, the integral really would start from 0. So 0 to infinity of, then we'd apply Lotus, so we'd say y to the n, and then we put in the PDF of a standard exponential distribution, which is just equal to e to the negative y dy. Now that is not a nice integral for n is a general number, because you're going to have to apply integration by parts, integration by parts, integration by parts, and it's going to require quite a bit of thought to get that, and a bit of care to get that correct. So it's far easier just to now use the moment generating function, which we know the moment generating function of y of t is equal to 1 over 1 minus t. Now, we know that moment generating functions have the form, the sum from r is equal to 0 to infinity of the expected value of y to the r, t to the r over r factorial. So, and we also saw in the previous video, because of the Taylor expansion, we know that this function can be expanded in a well, we don't know that, but some functions can be expanded by their Taylor expansion, and they'll be equal to r is equal to 0 to infinity of the rth derivative of the moment generating function, evaluated at 0, times t to the r over r factorial. So we could begin taking our derivatives of this and try and get the value of this. But in fact, there's a better way to do this, which is to note that this is the sum of the, well, it's the limit of the geometric series. So the sum r is equal to 0 to infinity t to the r, i.e. it's 1 plus t squared plus t cubed plus t to the 4 plus t to the 5. The limit of that sum is 1 over 1 minus t, providing that the modulus of t is less than 1. And the reason for that, remember, is that if we call this this limit s, then if we multiply s by t, then we'll get 1 times t is t, then we'll get plus t squared, plus t cubed, etc. So if we take t times s and we subtract off s, then all the terms will go, except we'll have we'll have this 1, this negative 1. So we get negative 1. Then we can pull out s, and we'll get s times t minus 1 is equal to negative 1. So we get that s is equal to, multiply both sides by minus 1, and you'll get s is equal to 1 over 1 minus t. So that's why that is equal to the limit of the geometric series. Okay, yes, it's only valid for t is less than, the modulus of t is less than or equal to 1. That doesn't matter to us. We can, but the point is that we can expand this as this, at least on that interval. Okay, so we know that 1 over 1 minus t is equal to the sum, r is equal to 0 to infinity, of t to the r. Now we wanted this in the form, the sum, r is equal to 0 to infinity of t to the r over r factorial times the rth moment of the, we were doing y here, the rth moment of the distribution y. So, if we just multiply and divide by r factorial to get this here, we'll get the r factorial t to the r over r factorial, which implies that the expected value of y to the r must equal r factorial. So there we have it. There is the expected value of the r. Well, that's the rth moment of a random variable which is distributed by the standard exponential distribution, expo 1. Okay, and we now know that e of yr, the rth moment of the standard exponential distribution, is equal to r factorial. Okay. So now what we want to do is we want to use this to calculate if x is exponentially distributed with parameter lambda, then we know that x is equal to y divided by lambda. Then we would like to calculate the rth moment of this random variable, this general exponentially distributed random variable. Well, we can just fill this in and we'll get the expected value of y over lambda to the r. And then this is just equal to the expected value of y to the r over lambda to the r. Pull out the lambda to the r by linearity, and we get 1 over lambda to the r times the expected value of y to the r, but we have just calculated the rth moment for a random variable which is distributed standard exponentially. It's r factorial, so we get that it's equal to r factorial over lambda to the r. So that is the application of a moment generating function to calculate the rth moments of a random variable that is distributed exponentially.